Okay then, in this this question, this is question 11 from Booklet 1, Biological Molecules, and this is a question about inhibitors and enzymes. Okay then. So, in an investigation, the rate at which phenol was broken down by the enzyme phenol oxidase was measured in solutions with different concentrations of phenol. Okay, let's just think about that. So phenol being broken down, so phenol must be the substrate. It's always helpful to identify what the substrate is. The enzyme, well, it tells us that is phenol oxidase, and was measured in solutions with different concentrations of phenol. So the concentration of the phenol is the independent variable here. The experiment was then repeated with a non-competitive inhibitor. So you need to remember non-competitive inhibitors, they bind to a site away from the active site. Just abbreviate that. Okay, so when you're reading these types of questions, it's important to annotate them, or at least think about the different components of the information that you've been given. Okay, now this graph, on the x-axis it shows the concentration of the phenol. The independent variable is on the x-axis, see that is increasing. On the y-axis we have a measure of the rate of the reaction. Okay, so we're measuring the rate of the reaction. We can see broadly, or to begin with at least, as the concentration of the phenol increases, so does the rate of the reaction. That's what we'd expect. Increase the substrate concentration, the rate of the reaction will increase. Okie doke. So, in the first question, explain why an increase in the concentration of phenol solution from 2.0 to 2.5 millimoles per decimeter cubed has no effect on the rate of reaction without the inhibitor. So, above 2 to 2.5 without the inhibitor, we can see that there is no increase in the rate of the reaction. The reason for that is that the enzyme is working at its maximum rate. So, this is the rate, or the maximum rate is the maximum rate at which enzymes can form an enzyme substrate complex. So it's the maximum rate of formation of the enzyme substrate complex. Okay? They cannot collide any more often to form an enzyme substrate complex, and therefore the speed of the reaction is limited here. Okay? We can say that the active site of the enzyme, is saturated. Okay? So as a substrate enters the active site, as soon as the products leave, another substrate will enter. The active site of the enzyme is saturated. Now, whilst it doesn't really ask you this in the question, if you think about it, to increase the rate of that reaction, you would need to increase the concentration of the increase the concentration of the enzyme. Okay. In the second part, explain the effect of the non-competitive inhibitor. Well, as we've already annotated it here, we saw a non-competitive inhibitor. we thought about what does that mean. So it binds to a site away from the active site. That's our first mark. The inhibitor binds to a site away from the active site. You see here, I've not abbreviated that. I've written active site. That's an important point. Sometimes you may see that site away from the active site referred to as the allosteric site. Your teachers may have told you that. They may not have done. A site away from the active site is fine. In doing so, when that inhibitor binds to the site away from the active site, it changes the shape of the active site so that the active site is no longer complementary to the substrate. And therefore, if it's no longer complementary to the substrate, that prevents the formation of enzyme substrate complexes. So there are 2 marks for this question. I've given you 3 points that would each be worth a mark there. Okey-doke. Now, although it doesn't say this in this question, one thing to note is that even with an increased concentration of the substrate, phenol in this case, you cannot overcome the effect of the non-competitive inhibitor. Let's make a little note of that here. So non-competitive, can't spell, inhibitors cannot be overcome by increasing the substrate concentration. That is one of the features of a non-competitive inhibitor. If it were a competitive inhibitor, if you continue to increase the concentration of the substrate, eventually you'll be able to achieve the same or the maximum rate of reaction. Okay, in this next question you're asked to calculate the percentage decrease in the maximum rate of reaction when the inhibitor was added. Okay, so to calculate percentage decrease in the rate, we need to know what that decrease was. Then we need to divide that by the maximum rate. And as it's a percentage, multiply that by 100. Now, if you'd just written that, you would get 1 mark for that, but for the 2 marks, you need to actually calculate it. So, let's look at the graph. You need to use a ruler for this. It's really important that you use a ruler because you need to read across to the y-axis. If you don't read across to the y-axis carefully with the ruler, it's likely that you would make a mistake, and there's very little tolerance for mistakes in reading graphs. So if you do that, you read across, you'll find that the rate without the inhibitor at its maximum rate was 7.6 arbitrary units. The rate with the inhibitor present, if you read across, is 5.6 arbitrary units. So we need to know the decrease in the rate. Nice and easy. 7.6 minus 5.6 divided by the maximum rate. Now the maximum rate we know, 7.6. Multiplied by 100 equals, I'll let you calculate this, 26.32%. Okay, so the percentage decrease is 26.32%, or 26.3 would be fine there. Okay, lastly, draw a curve on the graph to show the results expected if a competitive inhibitor instead of a non-competitive inhibitor had been used. Just to remind ourselves, the competitive inhibitor has a shape similar to the substrate and therefore is able to bind to the active site. That's why we say they're compete for the same active site. But, as I said a minute ago, by increasing the concentration of the substrate in the presence of a competitive inhibitor, you can overcome that competitive inhibitor. So, to answer this question then, draw a curve on the graph to show the expected results. Well, the rate would be decreased, but eventually it would reach the same maximum rate by increasing the concentration of the substrate. So you just need to draw a line below the rate with the without the inhibitor, but show on the graph that eventually, if you increase the concentration enough, it will still reach the same maximum rate. Okay, and that's worth 1 mark. Right, that's everything. Thanks.